Looks like this is working. Hi, my name is Philip, and I'm Director of Product Marketing for MSI Enterprise Platform Solutions. Today, I got a few minutes to talk to you guys about DCMHS architecture. We're going to look at what it is, the problems it solves, and how MSI is implementing this to solve these problems in the data center. But first off, DCMHS is an open specification that's been defined by a lot of members of the OCP community, and I want to thank everyone involved with the project because it's been helping a lot in server design. The specifications are publicly available, so if there's any questions after this, go to the OCP website. You can see anything I've left off. Before we get into what we're doing with it, we have to understand a little bit of brief history of the server CPU roadmap. If we go back not too long ago, there was essentially one server CPU vendor that mattered, and when you're doing server planning, you would just design around that processor, and that would be your generation of platforms. And it was easy. Eventually, we had another CPU vendor return, and now things got a little bit more complicated. You had twice as many boards you had to test, you had twice as many platforms you have to design, and as a customer, you'd have twice as many things you have to work on. Going forward a little bit, what we've seen is just an absolute explosion in the amount of platforms that we have to stay on top of as an industry. Now, not only do we have two main x86 server CPU vendors, but also they've got big sockets, they got small sockets, they got their mainstream sockets, they got their high core count sockets, and it's really difficult to know what type of platform you're going to design around. And it's not like our customers have doubled or quadrupled their testing resources either. So people are being asked to figure out what platform they're going to design their servers around with less and less resources. So if we look at how server motherboards were designed in the past, there were a lot of proprietary form factors. Things like ATX and SSI form factors were great because they standardized things, you could design your chassis around it, but we haven't used those in volume servers for a very long time now. So this has led to a proliferation of proprietary form factors, proprietary shapes, proprietary chassis. And that's fine. You might ask what's wrong with the proprietary form factor. You might have something that works. All right. What happens when the CPU socket gets twice as big? What happens when the amount of memory channels doubles? Maybe your tooling doesn't fit anymore. So the DCMHS design standardizes this, and it's been designed by companies who know the roadmap going forward and have designed these placements and these shapes which will last for generations to come. The other issue is that the BMC was on the motherboard. And this is fine if you have a server, if you have a motherboard. But if you have multiple vendors, you have multiple different shapes, you have multiple different form factors, multiple CPU vendors. If you're doing things like OpenBMC firmware development, you'll notice the BMC chip has a lot of multifunction pins. So the actual hardware implementation is different from board to board to board. So your hardware engineers, your firmware engineers developing your OpenBMC firmware, the amount of work that they have to do staying on top of the hardware specifics of each board, it explodes exponentially with the amount of platforms you have to support. So this is what I see as the future of server design, DCMHS architecture. It standardizes the shape. That's the first thing that makes it easy. Now we can design our chassis around form factors that we know we're going to stick around for a few generations. The thing that really catches my attention is the modular BMC architecture. So now no longer do we have the BMC on the motherboard. Now no longer do we have I2C pins going to random locations from board to board. Now you don't have to have a separate core OpenBMC firmware code base for each and every board and vendor you're working on. By putting it onto something called a DCSCM, Data Center Secure Control Module, now the BMC lives on this modular card. If you've got two CPU vendors, you use this on both of them. If you've got several ODMs, you can standardize it so multiple vendors use the same DCSCM. If you've got multiple server placements, same DCSCM. And the real benefit here, again, is if you're using OpenBMC firmware, the reason you're doing that is so you have the code base. The reason you're doing that is that your engineers can maintain your own firmware. The problem is you're maintaining your own firmware. So the more complex underlying hardware is, the worse it is. So again, by standardizing this, now you have one module that you use across vendors, across platforms, and it standardizes things. Something else this lets us do is we start looking at security devices like hardware roots of trust, and I have to pick something. Okay, maybe I picked the wrong one. Maybe I picked one hardware root of trust, and you have a project that requires something else entirely. Well, with the traditional motherboard design, where that would be on the motherboard, we would have to customize the motherboard. And then maybe you've got multiple vendors. Now you have to do this multiple times. You have different CPU sockets that need the special hardware root of trust. The amount of custom boards you need starts growing exponentially as well. So by splitting this off the motherboard and putting it onto a modular card called the DCSCM, It gives us the ability to make customizations, hardware changes around the server management hardware, and just implement it across the entire roadmap, across vendors, across CPU types, across boards, and now you're still using the same commodity off-the-shelf hardware. Basically, we're creating a building block approach for servers that we haven't seen since like the days of ATX, and those are still used in servers. So I'd like to transition to how MSI is implementing this technology in our roadmap. MSI over the past year or so has been transitioning away from a traditional ODM business model towards more of a white box, commodity off-the-shelf server design architecture. Luckily, when we came here about a year ago, we were given a blank check to start fresh and create whatever server architecture made sense to us. I wasn't limited to using old chassis designs. I didn't have to use old tooling. We're able to start fresh. And in my opinion, DCMHS is the future of server design. So MSI's entire product roadmap is based off of DCMHS architecture. And this does give me a building block approach. I can, along the top line, we've got DNO Type 2 host processor modules. These are half width that fit into compute nodes side by side in 19-inch chassis. In the middle, we've got DNO Type 4 host processor modules. These replace what would have been extended ATX or eATX boards in the past. The extra width allows us to do things like support 24 DIMM slots. It allows us to do things like have 2 OCP NICs. I can put this into a 1U chassis, and I can have 3 expansion slots plus 2 OCP NICs. I can do 5 expansion cards in a 1U chassis with this form factor. And along the bottom is our full width, or the MFLW host processor module. And this is what we use for dual socket host processor modules. And this is what I have this generation, but going forward, we're going to be using this architecture for generations to come. So chassis I design now will support these in the future. And customers who base servers off these platforms, any of the mechanical validation they do to make sure there's no sag and bow in your chassis, make sure that things not going to fall apart, that mechanical validation you're doing for this generation will carry forward to future generations because we just rip the CPU socket out and put the next one in when those come around. And the DNO form factor gets spun into something called SDNO next generation, but it's the same basic form factor. The Type 2 DNO host processor modules live in a series of multi-node compute chassis in a product line that MSI calls Core Compute. And this takes that Type 2 DNO Type 2 host processor module and it puts it into a multi-node compute chassis. And I can essentially scale up and down density based off your rack power budgets. For extreme high density, say you got a 60 kilowatt rack, I can liquid cool a 2U4 node with 500 watt processors. So you got something more pedestrian with, say, a 34 kilowatt or a 30 kilowatt rack power budget. Then you're in the 2U2 node territory, and now you're air cooling 500 watt processors. Say you've got something more reasonable. You've got like a 12 kilowatt, 17 kilowatt, 8 kilowatt rack power budget. That's when you end up running out of power way before you run out of space. And I see a lot of racks that ship with just mostly blanking plates. And in my opinion, anytime you ship a rack that's full of blanking plates, that's a failure of planning. So you just, those blanking plates could have just been taller heat sinks with just fans that don't have to work as hard. So my 3U2 node chassis lets me basically fully populate a 42U rack at 17 kilowatts, even without storage, just processors. You're running out of power and space at the same time. And we're seeing fan power consumption numbers in a compute node configuration with node drive bays around like 30 watts per node. So it's very efficient once you scale up to the 3U2 node chassis. And the way we've done this also is that we've architected our entire chassis. My entire roadmap is using what's known as an extended volume air cooler, or Evac. Nothing too special here other than the fact that we've done the planning in advance to make sure that these Evac heat sinks fit. And that becomes a problem too, where if your heat sink stays within the keep-in zone of the CPU socket, you don't have to think that much, it just fits. But once the heat sink starts to extend beyond the socket and starts occupying parts of the chassis, you have to make sure that there's open volume there for the fin stack. You have to make sure there's not cable connectors in dumb places that's blocking the heat sink. You have to make sure there's no brackets in the way. And so with our platforms, we started with the heat sink. We drew the heat sink first, and we put the chassis around it. And this is a 2U4 node system here, but the same idea in the 2U2 node. You got a remote fin stack extending both sides of the socket. The 3U2 node is the same way. Our basic architecture is like this. Previous multi-node designs used to put the motherboards at the back next to the power supplies, and that worked when sockets were small. You didn't have many DIMM slots. CPU sockets are still large now, and you have so many DIMMs that doesn't work. So now the motherboards, the nodes go in front of the power supplies. You also get front I/O, so that's great for cold and hot idle containment. So you got front I/O, rear power, rear fans. And due to my modular building block approach using host DCMHS architecture, we support all the mainline server processors this generation, and we will continue for generations to come. You just take that host processor module out, we drop in the one with the CPU once. We do that. We offer them as products. It's not something that the customer does, but it enables us to be flexible and offer basically any CPU that's on the market that would be reasonable in this type of chassis. Our enterprise platforms also use DCMHS architecture, all of them at this point, and going forward as well. We got 2U chassis with 24 drive bays, we got 1U chassis with 12 drive bays, and they're designed around the Evac heatsink concept as well. And you can see how you kind of have to do your homework in advance before you start doing your chassis tooling to make this fit, but it lets you do interesting things like in a 2U chassis, you've got space for full-length PCI Express cards, you've got space for GPU cards that need to sit on the upper half of the chassis. The heatsink will be 1U, but it extends forward and out and up, and that way you still get the full volume of your heatsinks even with long PCI Express cards. And so their entire roadmap, again, is using this. And this will be wrapping things up a little bit early. Just the message here is that MSI is very thankful to the OCP community for defining DCMHS architecture. It really makes it easier for us to standardize server design for generations to come. And due to the way it disaggregates management from the rest of the motherboard, it allows us to be flexible for customer demands, for custom hardware. It allows us to better support things like OpenBMC. These are all in development right now, but the platforms we went over today will be launching towards the end of this year and early next year. They'll be available through standard distribution, but my goal with these products was to get like 90% of the way to any customer projects, and then we can just depopulate from there to meet specs or cost targets. But anyway, that's all I have to say. I hope everyone learned something, and I hope everyone enjoys the show. Thank you.